Hello, and a warm welcome from my side. My name is Kostas Chinarakis. As Communication Officer of DGE-ROLLOUT, I have the honor to guide you through this event. DGE-ROLLOUT is an Interreg project of the European Union. Our vision is to foster deep geothermal energy as a climate-friendly heat resource in Northwest Europe, and subsequently nurture the region's economic and the well-being of the citizens. To achieve this, we do not only want to generate expertise, but also make it available and provide information for stakeholders and investors of geothermal energy. Therefore, I'm very pleased that so many of you have joined our webinar today, and I'm sure you will take away useful insights. I'm very happy to welcome today's speaker, Arianna Passamonti from Fraunhofer IEG. She's an expert on thermodynamic converters. Arianna holds a Master of Science in Energy Engineering from the Politecnico di Milano. She spent 2 research periods in overseas, 1 year at the Korean Advanced Institute of Science and Technology, and 1 year at the University of Guelph in Canada. After having worked in industry as product manager on boilers, heat pumps, and solar thermal systems for Bosch, she joined Fraunhofer IEG and the project you will now learn more about. So I'm very happy to welcome Arianna Passamonti. Arianna, the floor is yours.
Thank you very much, Costa, for the kind introduction and the organization, and welcome everyone also from my side. Today I would like to talk about how we can exploit the usage of water that is contained in former coal mines for high temperature heat pumps as a geothermal application. So I will give an introduction on what is our motivation to do so, and then I will talk about how geothermal heat sources are connected with geothermal heat pumps. And then I will go more into details on the DGE-ROLLOUT project itself and what we are developing in Bochum in Germany as our pilot plant. So I will give the objective. And then in terms of heat pumps, the state of the art of high temperature heat pumps, examples, and the heat pump model that we will install. And also I will talk about the heat source and the heat sink. The heat source, as you might have understood, is a former coal mine, and the heat sink is the district heating. And then I will give some conclusions and an outlook. So for what concerns the motivation behind this project, I thought of dividing it in 2 parts, one on the European level and one on the German level. So for what concerns Europe, and in particular Northwest Europe, that you see here represented in red in the maps, that is the area of our Interreg project. You see that these areas are urbanized and densely populated. And as you can see in the map on the left, they have the highest thermal energy demand in the EU. So you can see on the left the heat demand density of these areas, both for residential and industrial processes. So the heat demand there is very high. On the other hand, there are the European 2030 targets that aim at reducing CO2 emissions from fossil fuels in electricity and heat production. So as you can see to the right hand side, we have represented the coal power plants, and the gray are the ones that are shutting down in these years. And you can see that they are many. So on the one hand, we have high thermal demand, and on the other hand, we have lower production from coal power plants in the next years, and already existing district heating grids. So we need to find a solution for that. And Bochum is where we are located, and we are exactly in the middle of it. So this is one first point on the European level. And on the German level, we have the phase out of coal in 2038 and the closure of nuclear power plants this year. And you can see here the heat generation by source. You can see that, of course, the coal is decreasing. And you can see, however, that the natural gas production is increasing because this is a very fast solution, let's say. And the nuclear, on the other hand, has been pretty low for heat production. And you can see that also geothermal is also can improve a lot and, let's say, take a part of the coal and the natural gas. So here you can see also that the fact that the coal power plants are closing doesn't mean that that's the only, let's say, consequence of the phase out of coal, but there are also in our area many former mine shafts that are not being used. Here you can see just in the Ruhr Valley, it's about 1,000 that are here represented. And you can see that they are many. And they are flooded, and sometimes it's also necessary to have pumping. So this could be exploited as heat sources. So to conclude the motivation, we have need for low environmental impact in the heat production. We already have existing diffuse district heating grids, especially in Germany and in this area. And we have a large amount of flooded former coal mines. So what we thought of doing is to use geothermal for this and geothermal applications. So I would like to talk about, in general, a bit about the combination of source and applications, and then what we are doing in particular in Bochum. So we know that this is just I don't want to generalize, but to give an idea that when we have a source, a geothermal source that is of a higher temperature, we can either do direct, so electricity production, or have direct use for heating and cooling, for example. But if the source is at a lower temperature, let's say below 90 degrees, then we could use it either directly or use heat pumps. And the lower the source, the more, let's say, importance heat pumps have. So in our case here for the mines, we are talking about, in the case of Bochum, of 10 degrees, for example. And in this case, heat pumps really have an importance. But also if you have a deep geothermal and you have a source with an expected temperature, but its temperature is not satisfied, then you can use heat pumps to increase the temperature. This could also be a very good application. So geothermal heat pumps are, let's say, the ones that we are talking about are in the end similar to the ones for residential applications. And the geothermal part of it, that is the part represented at the bottom of this picture, can have different configurations. So we can talk about closed systems or open systems. Closed systems are, for example, borehole heat exchangers or horizontal configurations, but that are in the case of, for example, a dry source. But if we have a water body, we could use open systems. And this is the thing that we are doing in Bochum. So we have two wells that you can see here represented to the right. And these are the wells that are used for the heat pump. So this is our case. We have the two wells, the heat pump. We also have some solar, and then we will connect to the district heating. So to enter more then in details about what we are doing exactly, we are developing a test site for high temperature heat pumps coupled with the seasonal high temperature mine thermal energy storage. That is the source of our heat pump. We are doing this through two different projects. One is, of course, the DGE-ROLLOUT that is involved in the heat extraction part in the project, because it's a seasonal storage. So we have heat injection in the mine and then heat extraction. And the heat store that is for the part of the heat injection into the mine. So here you can see then, still talking about seasonal, the summer operation that is from a concentrated solar power plant. We want to inject heat into the mine that is situated exactly under our offices in Bochum. And then the heat that is stored there, we want to use it in the winter or in the heating season with a high temperature heat pump and connect it to the district heating. So it is important to notice that it's high temperature heat pump because the district heating requires these temperatures. So we are in the, let's say, scope of substituting the existing coal power plants. So this is our example here. And then since I thought maybe not everyone knows what is a heat pump, I also would like to just give a reminder of what it is. So the heat pump that you can see represented here with the components to the right is a thermal machine that has the goal to transfer heat from a lower temperature heat source to a higher temperature heat sink by means of mechanical power, for example, of the compressor. So here you can see that there is a cycle in which the refrigerant runs. And starting from before the compressor, we have lower pressure side. The compressor increases the pressure of the refrigerant, that is in this case in a gas phase, and then goes through the condenser, giving heat to the heat sink and is condensated. After that, it is expanded, so it goes to the lower pressure level, and it goes through the evaporator, where it evaporates and gets heat from the heat source. So this is the cycle. In our case, the source is the mine and the sink is the district heating, and I also represented like very, let's say, schematically also the powers that we are considering. So we have power from the source of about 200 kilowatt, 100 kilowatt electric power, and then here I put, let's say, as approximately 500 kilowatt of power production. So here you can see that there are two main constraints that are the ability, let's say, to reach 120 degrees as supply temperature, but also being able to reach 500 kilowatt. This is our target. And then after that, I went to the market and I had a look what was possible there. And here you can see that there are about more than 20 models of heat pumps achieving supply temperatures higher than 90 degrees, but there are only few able to exceed 120 degrees. And the power, on the other hand, varies a lot between few kilowatt to about 20 megawatt. This was in 2018. And here you can see in the graph that you have in the y-axis the maximum supply temperature, and on the x-axis the capacity of different models of heat pumps, and the different colors represent the different compressors. So in our project, we are situated here, I would say. So you can see that it's not a lot available on the market at the moment. On the other hand, there is a lot of research that is being done on the topic. So you can see, for example, a prototype from 2021 by Sintef, and it is high temperature heat pump running with water as refrigerant and has elevated powers, but also reaches up to 180 degrees. So this is also possible to reach up to 180 with heat pumps. Here I reported some examples of existing models. You can see here from Fraunhofer and German CO2. They have two different cycles, one with R134A and one with R744, that is CO2. And they both, however, reach up to 90 degrees, so these were not possible for our case. Then if we continue, we can see a hybrid energy that has a solution that is between a compression-driven heat pump and an absorption heat pump. But as in this case, they reach up to 110. That was too low for us. And then there are other solutions such as Oxner, but we excluded it because we wanted specifically to have, for example, natural refrigerants that for us are very important for, let's say, the long-term behaviors and so on. And also we wanted to have a reciprocating compressor that for us is important because they can be optimized for lower flow rates, for lower powers, so we can test our heat pump in different conditions. So this, of course, was also very important for us. So the best solution was with Johnson Controls. So we are really happy that this was the solution that we chose and that we found. And it is two heat pumps in series, one with R707, that is ammonia, and the higher temperature stage R600, that is butane. So this really supplies or follows all our requirements, and it will be installed in the next couple of months in Bochum. So this was the heat pump. Then I thought it was also very interesting, the mine, because it's a particular heat source for the heat pump. And the mine, you can see it here at the right. It is situated directly under our buildings, that are these three buildings here of our offices. This is Bochum, so here there is the Hochschule, and the university is over here. It is a shallow mine that has a maximum depth of 75 meters, and the groundwater level is at 23 meters below ground. The unheated temperature is 12 degrees, and what we want to do is with the solar to heat it up to 60 degrees. And the mine had only a couple of years of production. It was one of these mines that was, let's say, started after the Second World War, when there was a need of coal quickly. So it was just a couple of years, and it's shallow. And then we know the amount of coal that was extracted in terms of tons. And it's also possible then to evaluate the volume of coal that was extracted. And with some assumptions, we came to the amount of water that is now contained there. That is about 20,000 cubic meters. So this is our heat source. For this, as I said, so it was developed during the heat store project, and we did. For this, I have to thank my colleagues. So first of all, Florian Hahn, that worked on this project, and we made some modeling with our partners of Delta H for the groundwater flow and heat transport. So you can see here on the right that we have the shafts and the drifts of the mine. We have in yellow the two wells. And we can see after 2 years the production and the injection wells and how they behave after 8 years. This is due to the fact that we have cycles of heating and, let's say, cooling down of the mine, and the fact that the rocks after years help with the heat, let's say, to contain the heat. So after the simulation, we decided what would be the best drilling spots, that are the yellow ones, and also here represented on the view from the top. So we drilled the production, the injection, and the monitoring well. Here are always our office buildings at the bottom left in the picture. And here you can see our drilling rig with which we drilled the wells in the summer of 2020. And after drilling, we did some tests on with different pump tests on the different wells. So starting from 1 cubic meter per hour up to 7 cubic meters per hour. We did heat injection and heat extraction tests. For this, I still have to thank the colleagues from the heat store. So you can see here the results of the heat injection and extraction tests. So here they were done on this monitoring well. You can see in red is the temperature variation, and in blue is the water level. So we want also to have a constant water level. And you can see that we did a heat injection test at the beginning of December for a couple of days. Then we stopped because of the weekend. And then we did another test here. And after stopping, the temperature decreased. Then we did here at the beginning of February some heat extraction tests. So this behaved as we expected. Here to the right, you can see a picture of the heater that we used for the tests. This was just for the tests. Now we are using the solar. So this is some results. This is the solar that we installed. It is parabolic trough collectors, and there are 12 collectors on 2 rows. We have a total heat capacity of 60 kilowatt, and we have a temperature level. Here is written between 100 and 200 is the general, let's say, values for this source, but we have at the moment around 90 degrees. We want to stay below 100 because of the construction of the plant. And here you can see how it looks like in practice. So this was the total of the heat source, and then we will connect our heat pump to the district heating of Bochum South, so that the existing district heating grid. The characteristics of the grid are here reported. So the temperature, supply temperature is between 80 and 120 degrees. Here you can see in the graph that we have a temperature of 80 degrees when the ambient air temperature is above 8 degrees. So when it's warmer, the temperature of district heating is lower. And when it's colder, so below -10, we have 120 of supply temperature for the district heating. And then we have a linear behavior between. The return temperature of the district heating is always between 60 and 65. And the total capacity is 115 megawatts. So this is really optimal for us because we have the possibility with 500 kilowatt of heat pump to test it as we want, because for them it's sort of negligible at this time. And here is a view from the top. So here is again the university, the Hochschule, and here is in blue our buildings, inside the blue square our buildings. And we want to connect at this point here where there is the district heating grid, and there is an underground tunnel that we will use for that. So this is the connection to the district heating. And just to conclude, I wanted to say that so we are developing this pilot site, and so as described within the project Heat Store that was already finished and in the DGE-ROLLOUT, and that we believe that heat pumps or high temperature heat pumps are technologically ready to substitute fossil fuel fired power plants in district heating and industrial applications. So this is really important for this, let's say, energy transition. So, and this, for this, I would like to connect them to the outlook. That is that with the project's development, it will be possible to prove the exploitation of abandoned mines as heat storage facilities, but also that coupling them with heat pumps will enable the energy conversion towards the CO2 reduction goals. So of course, this is not the only solution, but this is a help that we can get. So yeah, this is the end, and thank you very much for your attention, first of all, and then I would like to thank also the colleagues that worked on this, so Florian Hahn, Matthias Udry, and Frank Strosig. So thank you.